Okay, so let's look at a common limit that it is L'Hopital's rule, but it takes a little bit of manipulation to do. And this limit, let's write it down. You'll think, oh, I see it in this class, I'll never see it again. No, it's going to pop up in calculus 2 as well. So, let's say we have the limit as x tends towards 0 from the right of x, natural log of x. Okay. So this is of the form of 0 times negative infinity. The limit as x tends towards 0, the natural log of x. This term right here is tending towards 0. That term right there is tending towards negative infinity. Okay. So, we can only use L'Hopital's rule if it's in a fraction form. And we don't even have a fraction right now. So let's force it to become a fraction and then try to evaluate the problem. So I could rewrite this thing like this. Now, this problem, all right, so I forced it into its fraction form. And so at this point, I can say, you know, this guy's going towards negative infinity. And remember, if you have a constant divided by 0, and this is headed in from the right, so it's in the positive direction, this is going to head towards positive infinity. So that's going to equal the limit as x tends towards 0 from the right. Now remember, the derivative of the natural log of x is just 1 over x. Okay. Now the derivative of 1 divided by x. You can think of this as x to the negative 1 power. So what's it going to do? It's going to spit out a negative 1 and it's going to drop it down to negative 2. So this would become negative 1 divided by x squared. Right? See, normally when I think about this problem, I just think about the bottom fraction flipping upside down. And that's perfectly fine if you want to think that way. But if you struggle a little bit with fractions, think that I need to get that x squared off of the bottom of this problem. Okay? So I'm going to multiply this by 1. Just x squared divided by x squared, because this x squared is going to knock that guy off. And so that will equal the limit as x tends towards 0 from the right. Now x squared divided by x would just be x. It would be divided by negative 1. Okay. And so at this point in the problem, we can just say, well, that's 0 divided by negative 1. So 0 divided by negative 1 is just going to come out to be 0. Like that. Okay. Okay, so you kind of think that, well, this problem can't show up again. Yes, it will. So, let's say all right, so that's just a precursor to other problems. So if I was looking at, let's say, the limit as x tends towards 0 of x raised to the x power. Okay? Well, I don't know how to tackle this one yet. So what I'm going to do is I'm going to say, well, I'm going to let's just let it equal L and let's take its natural log. Say this is L. Okay? So the natural log of L, which would equal the limit as x tends towards 0. You know, let's just make this from the right for consistency. the natural log of x raised to the x power. That would be the limit as x tends towards 0 from the right of x, natural log of x. Okay. All right, now this is the same problem we were doing just a second ago, but now we got to this part, we need to put it in fractions form again, just like the previous problem. So that would equal the limit as x tends towards 0 from the right of the natural log of x divided by 1 over x. Move them up a little bit. So this guy would tend towards negative infinity. This guy would tend towards infinity. So at this point of the problem, we can apply L'Hopital's rule to our limit. So that would be the limit as x tends towards 0 from the right. Now 1 divided by x over negative 1 over x squared. Okay. And you'll saw in the previous problem how I can multiply by x squared divided by x squared. That step is not necessary. Let's just say we're going to flip the guy on the bottom upside down, and so that the top will become x squared divided by x. Okay. So that would equal the limit as x tends towards 0 from the right of x divided by negative 1, which would equal 0. Okay? But pause there for a moment and think about what this statement says. So, what do I have here? I have basically a long sentence that says that the natural log of L is going to equal 0. Okay? That's fine. So, if the natural log of L is going to equal 0, so to undo the natural log, I would raise both sides above e. Okay? So this would imply that L equals e to the 0, and e to the 0 is just 1. Okay? Well, this problem couldn't possibly come back again. Could have? Well, yes. All right. So, well, I mean, this is not the exact same problem. It's one that just has a similar property to it. So, we'll look at our classic problem. Let's say the limit as n tends towards infinity of 1 plus 1 divided by n, now raised to the n power. Right. We're going to use the same type of logic on this one. So we're going to say, all right, I'll let it equal out. Why not? So let's take the natural log of that. So the natural log of L is going to equal the limit as n tends towards infinity of the natural log. All right, this is going to be 1 plus 1 divided by n raised to the n power. Okay? And we're taking the natural log of that problem so that we can pull the n to the outside. Okay, so that would equal the limit as n tends towards infinity of n times the natural log of 1 plus 1 divided by n. Right. Okay, so this is kind of like the problem we were doing a minute ago, except in the previous problem we had the limit as x tends towards 0 of the natural log of x. Okay? And so that problem was like 0 times negative infinity. Well, in this problem, we're sending n towards infinity. So this guy is going to infinity. This term right here is going to 0. So this looks like the natural log of 1. Okay? And the natural log of 1 is 0. Okay? So let's turn this into a fraction but in a slightly different way. So let's pull that in down to the bottom. Like that. Right? So now when I look at this problem, if I send n towards infinity, well, 1 over n is going to go to 0, and so the top looks like the natural log of 1, which is natural log of 1 is 0. Okay? 1 over n, if I send n to infinity, well, this guy is going to go to 0 as well. So now, since I turn it into a fraction form, I'm going to have 0 divided by 0. So that guy's headed towards 0. That guy's headed towards 0. Let's apply L'Hopital's rule again. But let's apply L'Hopital's rule. We haven't done it yet. Okay. So we're going to have to take the derivative of the top and the bottom of this problem. Okay. Now remember, when you take a derivative of a logarithm, what is it going to do? It's going to force whatever is in the logarithm down to the bottom of the fraction, and then we're going to have to multiply by its derivative to obey the chain rule. So the first thing that's going to happen is that 1 plus 1 divided by n is going to be just forced to the bottom of the fraction. Okay. Big fraction sign right there. Okay. So right now I'm only considering the derivative of the top of this one. All right. So if I take the derivative of the natural log, it forces it down to the bottom of the fraction. And now I have to consider that I have to obey the chain rule. So the derivative of 1 is just 0. Okay. Taking the derivative of 1 divided by n, well, the derivative of 1 divided by n, we think of this as n to the negative 1 power. So what is it going to do? It's going to spit out a negative 1, and it's going to drop it down to negative 2. So that becomes negative 1 divided by n squared. Because that's the derivative of 1 over n with respect to n. Okay. Well, if I take the derivative of 1 over n, which is the bottom of this thing, that's also negative 1 over n squared. Okay. Well, those guys are going to cancel each other out. And, well, we end up with just a limit as n tends towards infinity of 1 divided by 1 plus 1 over n. Okay, so I'm taking the limit as n tends towards infinity of this thing. So this guy right here, at the bottom of the fraction, that 1 over n is going to go to 0. Okay? So what am I left with is just 1 divided by 1 plus 0. Well, 1 divided by 1 plus 0 is just 1. Okay, so once again, think that this is a long statement saying that the natural log of L equals 1. Okay. Well, the natural log of L equals 1 implies that L is going to equal e to the 1. And so that's how we get the limit as n tends towards infinity of 1 plus 1 divided by n equals